Good afternoon, everyone. Thank you for joining us today, and thanks to the Data Science Festival for organizing the event and having us speaking with you today. So Chris and I, we want to talk about building and deploying reproducible machine learning pipelines. So we're going to discuss what are reproducible machine learning pipelines, what are some of the challenges that we can find, and what are potential solutions to those challenges. So, as we were introduced already, I work as a data scientist in LV, and Chris works as a software engineer in Babylon Health. We used to work together in a peer-to-peer company. That's how we met. And then we team up to build this course that is now live on Udemy, and where we teach how to build and deploy machine learning models. And today, we're going to cover some of the content that we have in this course. Specifically, we want to talk about deployment of machine learning models. So what is model deployment? We also want to talk about machine learning pipelines. What are machine learning pipelines? We want to talk about reproducibility and why it matters when we're working in organizations. We're going to cover some of the challenges that we can find to achieve reproducible pipelines. And then we're going to propose one architecture solution to achieve reproducible pipelines. And finally, we're going to cover how to test our models before putting them in production, before releasing them so that they can score our customers. So diving straight into it, what is model deployment? So model deployment means putting our models in a production environment so that they can actually start scoring live customers or whatever product we have. And when we put the models in production, when we deploy our models, is when we start getting true value of our models. So that's why model deployment is a key part of a machine learning pipeline, and it's often the most challenging part of the pipeline. And this is because it involves the collaboration of several teams across the business. So it involves the collaboration of data scientists, DevOps, software developers, and also the business professionals, so that we make sure that the model that we put in production is sound, and it also fulfills many of the regulations that we need to follow. So what is a machine learning pipeline, and why are we not talking just of machine learning models? So a machine learning pipeline is, in essence, the series of steps that need to occur so that we get predictions out of our data. So a typical machine learning pipeline involves steps like collecting the data and then transforming the data using various data preprocessing techniques, and that it involves selecting features, building the models so that we can finally get the probabilities or the continuous outputs or whatever we can get out of this pipeline. So data gathering means making the data available first to our data scientists so that they can train our models, and then to the software developers so that they can reproduce these models in environment. And this data can come from several sources. It can come from in-house databases. It can also come from the cloud, or we can collect data from third-party APIs. So all of this data needs to be available in the various environments that I'm going to cover in a second. So then we have feature engineering. Feature engineering involves transforming our data. So typically, the data, as we get it from source, is never ready to use to train machine learning models. We have to do a series of transformations, for example, replacing missing values, encoding categorical variables into number, creating new features, extracting features from text. There's a lot of things that can go on here during the feature engineering stage. And then we need to select the most predictive features. And this is because the less features we deploy, the more likely our models are going to be robust, and the easiest the process is going to be. And feature selection typically can occur together with training our models, and then we can get the probabilities out of this. So what is reproducibility in machine learning model? In machine learning. So reproducibility is the ability to duplicate a machine learning model exactly such that same inputs come in, same outputs come out. So from every machine learning pipeline that we have, provided that the same input come in, we need to make sure that the same output come out. But reproducibility between what? What am I talking about? So why do we need reproducibility? So typically, when we work in an organization, we have more than one environment. So we have at least the research environment. So here is where the models are born, if you want. So this is Typically, in many organizations, this is done in Jupyter notebooks, where the data scientists get the data, do the analysis, find the information, transform the data, select the features, and build the models. So this, as you can see, is the first machine learning pipeline. So then, when we want to put these models in production, when we actually want to use them, we need to put these models into the development environment. And this is when the software developers come in and try to reproduce all the steps that we have here into a new pipeline. And then here is when we are stepping away from Jupyter notebooks into proper software, typically Python scripts. It can be any other language. So here, hopefully, we will have a replication of this pipeline. So here you can see that we have the second machine learning pipeline. And then, hopefully, if all goes well here, we will deploy this into, say, one API or any other platform. And then this pipeline, again, needs to be identical. So reproducibility means that the models that we get here are exactly the same as the ones that we get here and the ones that we get here. So the same input comes in, same prediction needs to come out. And this is, in fact, very challenging. And we're going to see why in a second. But why is reproducibility so important? It's for various reasons, really. So the first one is that if our models are not reproducible between our research and production environments, this can incur in tremendous financial costs. And Chris is going to talk more about this in a minute. But imagine that if you prove the value of your model in your research environment, and then it saves you thousands of pounds, but then that model is not replicated in production, you're actually not saving your thousands of pounds. And then if reproducibility is not attained right at the beginning, you spend a lot of time trying to find out why your production environment is not getting the same models that you have in research. And it's also a loss of reputation for the team. But the most important thing for me is that without the ability to replicate exactly the results that we have, it is very difficult to determine if a new model is really better than the previous one. What are the challenges to reproducibility? We have challenges pretty much at every step of the machine learning pipeline. So the first challenging occurs at the stage of data gathering, and it's actually perhaps the most difficult challenge to reproducibility. And this can happen because we can't reproduce the training data set that we use to train our models. So often, we cannot reproduce the training sets between the research and the development environment. And why can that be? Variety of reasons. In some cases, databases are overwritten daily. So every time we update the record, we overwrite the record. So then the view that we have today of the data is not the same view that we will have in a month from now. So that already makes that the training data set is not reproducible. But there's also some technological techniques. So for example, if we're loading the data with SQL, so the rows are loaded at random. So we need to make sure that we order these somehow so that the randomness, we account for this element in randomness between the research and development environment. So this can have some potential solutions. The first solution is that we can save a snapshot of our training data. So then we have it, if you want, forever. It's very simple. This has a few limitations. Potentially, they have some problems with GDPR, because you need to be able to erase those records as part of the new GDPR regulation. And also, this is not suitable if you have big data and you have it stored in the cloud or things like this. And then you cannot easily store it somewhere else. So as an alternative solution, it requires to basically design the data sources with accurate timestamps. So this would be the ideal situation, so that you can retrieve a view of the data at any time point in time that you want. So if you know that the research occurred today, when we train the models, we will get the view of the data from today and not from 1 month from now. So this is the ideal solution, as I said, but if the data sources are not designed this way already in an organization, it involves a very big team effort to kind of reorganize the data sources. The second challenge occurs during feature engineering and feature creation. And this is because here, to engineer our values, we are getting a lot of statistical parameters from our data. So for example, we're replacing with percentage. So we're replacing with means and medians, or we're calculating percentages, or we're even using more complex equations. And sometimes we are replacing values with a random extraction. So the good thing is that many of these challenges get resolved by ensuring that the data is reproducible, the training set is reproducible between the research and development environment. But also, we need to make sure that our code is saved and stored and tracked under version control. So the code that we use to engineer these features, we want to track it. There are also challenges during model building. And this is because many of the machine learning models rely on randomness for training. So if we're thinking about trees, there are elements of randomness to extract samples from the data set, and there is also an element of randomness to extract features. If we're thinking about neural networks, the weights are initialized randomly. So it is very important to account for that by setting the seed right at the start. So whenever we start the project, we need to think about setting the seeds. And also, some libraries work with arrays, so the library has no idea what feature is going in each column. So it is very important that we need to make sure that we pass the data set always in the same order. So we need to record the order of the features. We also need to record the transformations if we're doing something else, or the hyperparameters, and so on. And this is usually done in a config file. So the final challenge to reproducibility occurs during deployment of machine learning model per se. And this is because often a feature that we thought we could use to train the model is not available in the live system. Also, sometimes we work with different programming languages, so we train things in Python, but then the business is working with Java, so we need to basically re-engineer the pipeline. And sometimes the populations that we get when we're scoring live do not match exactly what we thought we could get when we decided what training data to use. Some solutions to this is to basically, the software versions and the package versions that we use need to be exactly the same in the research and in the development environment. And we can use containers, basically, to containerize that and track these specifications. Whenever possible, it's good to research, develop, and deploy using the same language, for example, Python. This is not going only to ensure reproducibility, but also to smooth the process. And prior to building the model, it's a good practice to understand how the model is going to be integrated with our system so that we know exactly what population is coming in, what features are available, and so on. So now, what architecture can we build to account for this, to ensure reproducibility in machine learning pipelines? So here I'm going to cover one solution. This is definitely not the only solution, but this works quite well in organizations like finance and insurance and health. And the core of this solution is that this same pipeline occurs both in the research and in the production environment. So the same layers, the same structure is shared, it's not shared, but it's reproduced in research and in the environment. And the structure contains a data layer. So the data layer is where the data gathering occurs. And here we ensure that all our data is available both to the research environment for the data scientists, and the same data is available for the production environment. So they can both tap into the same data sources to ensure reproducibility. The feature layer, where the transformation comes in, shares the same software, both in research and environment. And then the scoring layer is where more transformations occur, like, for example, scaling. The models are trained and the predictions are made. And then we have an evaluation layer, where we not only evaluate the performance of the model, but we can also evaluate the equivalence of the models between this environment and this environment. And this is not about creating a whole pipeline from scratch. This is actually about leveraging the power of existing libraries that we have in place. So we all know potentially scikit-learn, TensorFlow, Keras, and other packages for feature engineering and other stuff. We ideally want to perpetuate the functionality that these libraries have. So whatever software we create to engineer features, we want them to fit in seamlessly with these libraries that we have here. And then we also use Docker to containerize and Git for version control. And we can also use another Python library that is very popular for evaluation of the levels. So because we share the infrastructure, the architecture between the system, the research, and the production environment, we're trying to maximize the probability of getting a reproducible pipeline. But this doesn't really end here. So we want to make sure, so we want to test that the predictions that the model that we train in the research environment match exactly the predictions that we've got in the production environment. And at least if they don't match, we want to understand and be comfortable of why is the reason that these don't match. And once we are happy with this, is when we actually push this pipeline into the live system so that we can start scoring our customers. So we can start sending the data and retrieving the responses for actually putting our model live. And before this happens, we are going to talk about, I'm going to leave you in the hands of Chris, where he's going to tell you more about what tests we can do before putting the models live.
All right, so Soledad's talked about some really important things when we're thinking about designing our machine learning systems. Now let's move on and think about just before releasing and some areas around that, particularly in testing. So first key point to raise is that at the time of actual deployment, it's already too late. And why is that? Well, hopefully this diagram is familiar to some of you. This is from a paper called Hidden Technical Debt in Machine Learning Systems, which was came out in the NIPS conference in 2015 from some people from Google. And basically, the gist of this paper was that with machine learning systems, you have all the challenges of traditional software engineering, plus a host of machine learning-specific challenges, things like data dependencies, configuration management, certain system design anti-patterns, and a host of others. And that diagram there basically shows you that in a typical system, your machine learning code is that small box in the middle, and then you have all these other components, each of which has to be designed and thought about in order to have an effective system. So Soledad's talked a bit about data collection and feature extraction. In the time I've got up here, I'm going to have a little bit of a look through some of the serving infrastructure challenges, and then testing, which underpins and needs to be done for all of these different components. So in order to do that, I'm going to first create a scenario to put things in a bit of perspective. So in this scenario, you have Jenny. She's a data scientist at a bank. And this is a finance example, but it could apply to countless other industries, from healthcare through to logistics, energy, the list goes on. So Jenny has created a new credit risk assessment model. The bank is going to use this model to determine what interest rates to give its customers when they apply for a loan. She's very happy with the model in the research environment. She passes it to her colleagues in engineering. They get it ready for production, and they release it to customers. All seems well. Time goes by, and in that time, thousands of customers receive loans. A third-party investor is sold part of the loan book, and the bank makes assurances to the regulator that they understand their risk. However, a few months later, an analyst finds that actually there's a feature missing. There's a bug in the model. And the specifics of this bug don't really matter, but to add some description to the scenario, let's say a feature for detecting student loans wasn't included, and so a customer's everyday spending, lifestyle spending appears higher than it actually is. And what that means is they're going to be getting a higher interest rate than they should be. So Jenny's got to go to the CTO and the CEO and explain that. They've then got to go to the regulator and say, sorry, we were wrong about the risk that we told you about. They've got to tell their customers. They've got to tell the people who've bought part of the loan book. This is a bad day at the office. So what can we do to avoid a scenario like that? We have a spectrum of options. And to begin, let's look at everything before production. So we have here a host of usual suspects, different testing techniques, unit tests, integration tests, acceptance tests, BDD tests. Hopefully, a lot of these are familiar and being used in your companies. But there's a more exotic sort of test called differential testing that I want to spend a bit of time showing you guys. Differential testing, also known as back-to-back testing. I think differential testing is a more useful name for describing what it actually does. And this is a diagram to let me walk you through what exactly happens in differential testing. You generate a significant test input data sample, 10,000 rows, 100,000 rows, depending on the sort of model that you're testing and how difficult it is to generate that data. And you pass it to your current in-production model, and you pass it through all the sort of data pipeline and data munging, feature engineering sort of steps of your pipeline that Soledad was just talking about. And then you take the outputs from that current model in production, and you keep them ready. And then you apply the same input data to your new candidate model, so V2 here in the diagram, and you look at the outputs, the predictions from that new model, and then you basically do a diff on the outputs. And you're looking for if the difference has changed beyond a certain average, could be across the entire output, could be on a per row basis. And obviously you need to tune that depending on how big a jump it's been from one version to the next. If you've completely overhauled your model, then it's reasonable to expect a significant change. If it's a small version bump and you're seeing 5, 10% differences in the outputs, this can be a real cause for alarm. It could mean that a feature's been missed somewhere in the steps between research and productionization. It could mean that config's got an incorrect setting. The list goes on. But traditional tests won't catch that. Differential tests will. So there's some real value there. Moving on, we think about the production side of this spectrum. Some of you will be looking at the partitions there. Deploy, release, post-release. In a lot of organizations, deployment, releasing, shipping, these are all terms that are just used interchangeably. But there is a difference. When you deploy things, you can put the actual code into production without it affecting your customers. But then you can make the distinction when you release things, that is now affecting customers. And for an industry so obsessed with naming things, this is still surprisingly fuzzy, but the key thing is to understand the distinction, even if you use the terms in the inverse of what I've just described. And then we have post-release, where we do things like monitoring. This is already affecting customers, A/B testing, logging, all that sort of stuff, which would make for a good separate talk. So to kind of summarize that, deployment need not expose customers to a new version of your service. And some of you will be twigging now that what I'm talking about is testing in production. And this is what's known as a shadow deployment. Google also uses the term a dark launch. And this may be a bit uncomfortable as a topic, because there's certainly a school of thought that says, all right, if something's in production, then you should be testing it with monitoring. And that's in some cases very true. But particularly in the realm of machine learning models and testing there, this can add some extra value. There's also the argument that, hey, we should be just making sure that our staging or sandbox environments are completely at parity with our production environment. And that's definitely something that you should work towards, but there's some tough realities we have to face here. I mean, Soledad has already talked about the challenges of these different data sources you're going to be working with. If these are constantly changing, if they have seasonality, if they're from external sources that you don't really control, or complex documents, the chances of you really being able to create a total replica in your staging and sandbox environment with production, I mean, that's going to be an awful lot of work. I've not seen it done perfectly. And so shadow deployments offer us a way around this challenge. There are two ways to implement shadow deployments. The first is at the application level. So let me walk you through this. This is basically where you're actually adjusting your code to say that, OK, we've got V1, the existing version of our model, and we've got V2, which is in shadow deployment. And when the input data comes to your model that's been already through all the transformations and feature engineering, you're going to pass the input data to the existing model, and you're going to return the predictions, the outputs from that model, to your customers. You're also going to pass that same input data to your V2 model, but you're not going to return the predictions from that model to your customers. Instead, you're just going to store that information. You can store it in logs, you can put it into a database, but it's important that you are keeping track of it. And you can then leave that running for as long as suits your business needs and the sort of traffic you're getting, right? If you're in a high-traffic environment and maybe you can take a little bit of risk, then perhaps a day is sufficient. If you've got a very risk-averse sort of company, or you need to collect data for a long period of time, you can leave things running in shadow mode for weeks, even months. In the banking example I gave earlier, then perhaps weeks would have been ideal. So that's at the application level. And if I'm honest, this is a lot easier to do. It requires that if you're worried about performance, then you want to be thinking about doing the V2 predictions asynchronously, using a distributed task queue, or just spinning up another thread so that you don't block the request as it comes in while you're waiting for this V2 that isn't actually affecting customers. You also want to think about implementing feature flags. So you have a feature flag service, or feature toggle, some people call it, to allow you to control the flow without having to redeploy your service. The second way to implement shadow deployments is at the infrastructure level. So in this sort of case, you would configure your load balancer down at the infrastructure level to say, incoming requests, you're going to send the same request to 2 different services. Could be 2 different endpoints of an API as well. What that means is, though, that there are various other sort of more mature DevOps considerations you need to have. For example, you're now effectively doubling the load on your system. Can your system handle that? So there's some planning required around that. You also are going to have some challenges around, if you have alerting and monitoring set up, you don't want to trigger alerts on this V2 that isn't actually affecting customers. You don't want to wake people up at 3 a.m. getting paged. Also, you don't want to be creating customers twice. You don't want to be billing customers twice. So it does require a certain degree of DevOps maturity to operate shadow deployments at the infrastructure level, which begs the question, when would you do that? And there are a few scenarios. So the first is if you have a black box application, basically, for your machine learning. Maybe you can't touch the code, or you're paying for an external API service, and you can't actually go in and update the code, then that could be a good time to do things at the infrastructure level. There are also scenarios where you're prototyping your V2 model. Maybe you've written it in Python, but you have low latency requirements, and eventually you will rewrite it in C++ or a faster language. And yeah, first you want to prototype a bit. So that's another case where the infrastructure level might work. And there's also the scenario where your feature flagging configuration is just so riddled with technical debt that adding additional feature flags introduces more risk than you're willing to introduce. And that sounds like kind of a crazy scenario, but you'd be surprised how common that can be. Which brings us back to an alternative ending for Jenny from earlier. So Jenny discovers this bug in the model. She goes to the CTO, the CEO, and says, "We found this bug." And they turn white-faced in horror and shakily ask, "Have we got to now inform the regulator? Have we got to inform our customers?" And she says, "No, it's fine. Don't worry. Unfortunately, we've got to go back to the research environment and figure out what happened, but no customers are affected. You don't have to tell the regulator. This is a far better day at the office than in the earlier scenario." And with all the usual sort of conference caveats about there being no silver bullets, there are certainly times where shadow deployments aren't appropriate. Then this is really actually a shift change towards peace of mind, and that's something that I'm sure we can all agree is very valuable in doing our machine learning model in production. All right, that's the end of the talk. If you want to learn more about deployment of machine learning models, check out our course. Also, be sure to check out the Empower Namibian Community's neat booth downstairs. With that, I think we'll open up for Q&A. Thanks. Jonathan as well.
Thank you. And if you were here for the T-shirt shout-out earlier, these are the guys raising all that great money to do data science in Namibia. Anyone got any questions? We have about 10 minutes, and then we've got a coffee break. Yeah.
So you spoke about differential testing, but on your slide you also had soak testing, which I guess I would call Canary analysis. Can you speak a bit more about how they differ?
Sure. So for those who don't know, a Canary release is basically, it's another very good technique, but it's where you deploy your service to a small fraction of your users. Whereas in differential testing or in shadow deployments, you're ensuring that you're never actually affecting any customers. So Canary releases are another really useful sort of technique to have, but you are then starting to affect customers. So it's kind of the next step maybe you want to take if you're quite risk averse and you've been through your shadow deployment, you've been through your differential testing, and now maybe you want to do a Canary release.
Any more? No. Hand waving in the back.
Hi, Thanks. For the shadow testing you're talking about, right? So you have V1 model and V2 model. So my question is, my V2 model should be different from V1, right? And that's why I need a new model. But then how can I quantify? So it should be the V2 model I want, or some bugs in it, right? Because sometimes the bug can be small. It can be really hard to find it, right? How do you quantify that?
Yeah, I mean, that's where the challenge of the tuning that I was describing comes in. I think the real value with the differential testing comes in particular when you're doing relatively small incremental changes to your models, because by then, over time, you'll be gradually tweaking the sort of changes in average predictions that you realistically expect with this sort of model. It becomes quite a bit trickier when you're introducing a totally new sort of model. But that tuning process and like, okay, is it a 5% difference, a 10% difference, and figuring that out is something that kind of occurs iteratively over time. So for sure, like effective differential testing does require some time invested in the process.
Do I see a hand go up in this section? No. Anyone for any more? Oh, yep, over here.
Has there ever been an increase in malicious kind of exploitation of your models, maybe from a competitor?
I didn't quite get the question, sorry. Can you repeat?
Has there ever been kind of like probing attacks or kind of fake data being fed to a live model that you've been aware of, kind of like a malicious use of your customer endpoint for your models?
Well, I can just, off the top of my head, I'm sure there has been. I'm not directly looking into that, but I would expect that, yes, people are trying to figure out ways to game systems, understand how backends work and machine learning models work in production, especially if there's some sort of financial gain they can get from it. But I can't speak to any specifics.
Yes.
Solly?
So for the industries I've worked in, it's not like machine-driven hacking kind of thing, but it is true that people manipulate the data to try and get a different premium for insurance, or people that are impersonating someone else try to manipulate and put different information to try and bypass our fraud models. And it is true that they do learn how, but not exactly what variables we are using, but they get a feeling of what we are checking for impersonation, for example, so then they kind of revert it, and that's when we need to refresh our model. So it does happen, but not for our industries, like, serious firing of, that kind of thing.
Any more hands in the air? Nope. Oh. Hello.
Hello. Thank you for the interesting talk. Another question on the scheduled testing. So if I understand correctly, does it mean that you need extra resources because you don't want to expose these, say, machines to the real customers for the scheduled testing? And if that's the case, if we don't have the resources to support that, how can we get around it? And the second part is I don't fully get why do we need scheduled testing. What's the advantage over the traditional testing grid or the testing cluster? What's the main reason for that? Thank you.
So there's two questions there. Start with the first about resources. So just to distinguish, there's differential testing, which happens before anything goes into production, and there's a shadow deployment, which is actually putting code into production but not affecting customers. So with differential testing, then you're not talking about a major need for additional resources, a couple of extra containers, maybe an extra job in your CI pipeline. With shadow deployments, then yes, you do need to take into account that you're effectively going to be running the data through a second model and having to do all that work as well. So if you have a very intensive sort of model, then that can require some additional resources, but you're making that effort and fronting those costs in order to offset the risk that the model that you've just deployed has a bug that you won't be able to detect in your development sandbox environment, perhaps because the data you've got in production is just too complex for you to replicate accurately. And for the other reasons that we went through in the talk.
Yes, and if I can add something to that. So we are very thorough when we build our machine learning models, but at the end of the day, when we put them in production, we can never be absolutely sure that it's going to produce the result that we want. So by putting a model in shadow mode, we are actually live comparing what is our current result versus what is our new result. And if you're in a business in which that model is at the core of the business, then you actually want to be absolutely sure that your model is giving you what you want from it. So that's also the beauty of shadow deployments. Sorry.
Sorry, that was not intentional. Just one small question. I never used this concept of shadow deployment, but I've used a different concept with Canary deployment, which is a Canary deployment where you deploy for testing users on a production environment. Okay, so on that environment, typically, you might not have the full spec of the use cases when you test on your Canary deployment over your testing users. So the real advantage of a shadow deployment, is it that you can see the full picture over your full use case customers without having any impact? Is that the real world advantage over it?
That's correct, yes. There's actually two main reasons why you might do a shadow deployment. The first is what you were just alluding to, and that's what's really applicable in the context of machine learning. The second is if you want to do perhaps some load testing on your system in production. That's another perfectly valid use case for a shadow deployment.
Okay, time for perhaps one more. Any hands in the air? Yep, great.
Hi, thanks for the talk. Just a quick question. It's more like in the situation where basically there is a mismatch in the language used by the data scientist and the data engineer and the engineering side and software developers. So, for example, if you have a machine learning model that you want to develop, what you want to deploy, do you have any suggestions for a case, for example, where the software developers don't know Python, for example? That's what the data scientists use. And what would be better, like at some point there has to be a conversation what code to use, to deploy it. So would you rather have the data engineering learning sort of Python and understanding the data science language, and that's sort of an investment for the future because Python is what you use mainly, or vice versa, like it's better maybe that you use the knowledge of the software developers so the code will be stronger?
Yeah, I mean, you can look at it in quite a few different ways. I mean, it depends on your team and how willing they are to pick up new technologies. You can put a carrot in front of developers and say, like, if you don't know Python and you learn it, that's going to be a valuable skill. So there's always that. You also need to make sure that your developers and your data scientists are working really closely together so that things don't just get sort of chucked over the wall and forgotten about, right? You need to have teams collaborating effectively. I don't know, Soledad, do you want to talk about it from the data science perspective?
I guess that from the data science perspective, the key point in a scenario like this is to spend a significant amount of time trying to make sure that whatever you put in production is reproduced as much as possible into the new different language that we're using in research and production. I think teaching developers Python or teaching data scientists why not Java, because you can also make things in Java, is always an option, but it basically requires the business to change over the entire infrastructure. We usually come with some infrastructure legacy, so it's not always possible. Yeah. So as much as it sounds like amazing and ideal, we need to consider that as well.
Okay. Can we thank Chris and Soledad in the traditional way?